Hi, welcome back. Okay, carry on from the previous video about the torque and moment of inertia. I just want to continue a bit more on this particular aspect of A is equals to radius times alpha. So there's a relationship between the linear acceleration of the falling or the rising object with the rotation acceleration of the driving shaft. Okay, so it's related by this formula over here. Well, in fact, you can also go one order lower, meaning that instead of acceleration, you look at velocity, right? You will also have a very similar equation over here, formula. Okay, so this is a linear velocity of the object is equals to radius times angular velocity of the shaft. Okay, so alpha would be radians per second square. This is the unit. Okay, omega is radians per second. Please do not use degrees. Do not use degrees. Okay, the acceleration will be meter per second square. Velocity would be meter per second. Okay, and for this whole thing to work, you need to use SI unit. So radius will be in meters. Okay, so everything will work out correctly. All right. Okay, this is what we call kinematics. Things that we've related to speed, velocity, and distance. There are a few other kinematics equations that you should know as well. Okay, and you have come across them back in your secondary school. Okay, for example, V equals U plus AT. Okay, and you also have S is equals to UT plus half AT square. All right, and then lastly you have a V square equals to U square plus 2AS. Okay, if you notice, these are all linear components. Linear velocities, linear distance. Okay, in fact, there is a rotational equivalent. Okay, and it's just simply replacing them with the rotational counterparts. So for example, if V is a final velocity, right, then we will just use omega 2 to stand for final rotational velocity. All right, so U should be initial, right? Omega 1. Alpha will then replace A. Okay, so basically you just need to remember the left side. You can sort of find out the right hand side already. Okay, distance, this is linear distance, right? So for angular distance, it will be the angle. Okay, angle we will use theta. Again, this must be radians, okay, not degrees. So U will be omega 1t plus half alpha t square. Okay, and this will be omega 2 square, omega 1 square plus 2 alpha theta. Okay, so just remember one, you can remember the other. All right, and later on you'll be able to apply these kinematics equations. Typically they are at the end of the later part of the question. Okay, with that, let's look at one question from the tutorial 1.6. Okay, it is about this solid cylinder lowering a 15 kilogram cage. All right, 15 kilogram cage. 1.6. So it is a drum. Okay, lowering. Okay, so here you have your tension. The direction of motion. Okay, let's draw the cage first, which should be easier. So you have mg, and this is the tension. Okay, since it's going down, we define the acceleration to be pointing downwards. Okay, and since it's going down, we define the angle acceleration to be anti-clockwise. Okay, like this. Okay, must be the same direction. All right, and since the motion is anti-clockwise, the friction should be clockwise. Okay, opposing the motion. Give me a minute. Okay, I would have a unit of kilogram meter square. Okay, mk square, kilogram meter square. Friction torque is this much. Okay. Its acceleration during the lowering, it is 1 meter per second square. Okay, so it starts from 0. So you have to read the question carefully to be able to understand what kind of starting velocity and what kind of final velocity. Okay, so it started from 0. Okay, and it reaches 10 meter per second. Then it moves in a uniform velocity, and finally there is a deceleration. Okay, so in fact there are 3 stages later, which we will see, but now we can try to find out something else. Okay, how much time did it take during the acceleration process? Okay, with this you can use this. Okay, therefore t is 10 seconds. Okay, during the first stage acceleration, it took 10 seconds. The total distance covered, right, is 150 meters. Okay, find the radius of the cylindrical drum winch. Okay, this question is actually related to a formula in the lecture notes in page, let me see, one dash 3. All right, it gives a standard formula of I for different types of solid. Okay, for a disc, for a ring, for a cylinder. Okay, these are the formulas. Okay, so for this case it is a cylinder. Cylinder formula is half mr squared. Okay, so this is actually our 6.25. Okay, they are the same, 6.25. So with that you can find your r to be 6.25 2 times 6.25 over mass. Okay, square root. So you will get 0.707. Okay, why is this important? Because this is basically your radius over here. Okay, this is the radius here, which later you will use to find the moment caused by the tension. Okay, next, braking torque. Okay, so now we try to find our braking torque, but we have A, right? So we can find alpha. Okay, A over R. Okay, with this we can look at the both equations, sum of forces. Okay, let's look at the linear component first. Okay, so A is pointing down, so mg is positive. Okay, so no, sorry, C, sum of forces equals to ma. Okay, so it would be mg minus F is equals to ma. Okay, F is the only opposite direction, so it should be negative. So the tension is then mg minus A. Okay, and remember this m is the mass of the cage, which is 15, not the drum. Drum is 25. Okay, so there are 2 masses in this question, in a typical question. No, sorry. So this is your tension over here. Okay. After finding your tension, you can find the you can use this one already. Sum of torque is equals to I alpha. Okay, so the first one, then you look at the second one. Okay, sum of torques. So alpha is anti-clockwise. Okay, so the only anti-clockwise torque or the moment is from the tension, because it will cause this direction moment, okay, by multiplying tension to radius. So we will have F times R is positive. Okay, but the other two is opposing the motion, so it should be minus. Okay, equals to I alpha. Alright, so we have tension, we have radius, we need to find braking torque, and we have friction. Okay, we have I and we have alpha. So here you can find the braking torque. Okay, part C is the kinematics part lah. So there will typically be a so you have to draw a velocity time graph. Okay, and by the description there is usually an accelerating phase, a constant velocity phase, and finally a decelerating phase. Okay, so we can split this everything into three parts. Accelerate to 10, you know is 10 meters per second. Okay, and you know this one took 10 seconds. Okay, just now we found out already. Okay, what else do we know? We know that the acceleration here is 1. Okay, what else do we know? We know that the it moves with uniform velocity for 25 meters. Okay, it will be split into 3 stages, 1, 2, 3. So S2 is 25. Okay, we can easily find S1, and then we will be able to get S3. Alright, so S1, okay, S1 is equals to UT plus half AT square, which will give you 0 plus, okay, so this will be 50 meters. Okay, so because of this, S3 will be, we know total is 150, we just minus 50 and minus 25. The last phase is 75 meters. Okay, what else do we know? We can find out the time taken to reach from here to here, okay, by using this velocity and distance. So what is this? Velocity is equals to distance over time, right? So time taken is distance over time, 2.5 seconds. Okay, so this length is 2.5 seconds. Okay, so here will be 12.5. Okay, 12.5. Yeah, so these are actually all information that you can find. Okay, we want to find the final deceleration. Let's call this A3 here. We can also find, because we have 10 and 0 and distance is 75, so we can use the distance formula. Let me see, V square is equals to U square plus 2AS3. Okay, this is also A3 lah. Okay, V is final, is 0, U is 10. Okay, A3 we want to find, S3 75. Okay, so A3 eventually is minus 0.667 meters per second square, which is absolutely correct, because in order to decelerate, your A will be negative. Okay, accelerate is positive. Okay, that's the difference. Okay, part D. What is the braking torque required during the retardation? Retardation means this, the last part lah, part 3 lah. You can still use the original free body diagram. Okay, it doesn't mean that because A is negative, your direction is going to switch. No. Okay, you can continue to use these directions, but you just remember to put the A as a negative value. Okay, so let's look at this. At the last stage, your angular deceleration will be A3 over R. Okay. Minus 0.943, okay, radian per second squared. Okay, so let's look at the linear part first. The equation is the same. Okay, so now the new tension is how much? New tension is, let me see, 59.81. Remember to minus 0.667. Okay. So the new tension is 157.155 Newton. Okay, with this we can then look at the rotating component. Okay, the equation remains the same. Let me see, F times R minus TB minus TF. Why do I say it's the same? Because even as you decelerate, okay, the cage is still going down. Okay, your braking torque, you are still applying a braking torque, but this time the amount of torque is different. Okay, but the direction is still the same. Okay, minus 25 minus TB, 6.25 times. Remember the negative sign. Okay, and you will be able to get a new braking torque, 2 Newton meters. Okay, now then you can ask yourself, is this a correct answer? Logically speaking, it is, because you remember initially you are applying this much braking torque, right? 59, and that is during acceleration. But if you need the cage to be decelerating, you need to apply more torque. Okay, which you managed to get a higher value. So this is correct. All right. So the next video we'll talk about the other question.